Hello and welcome to another discussion on artificial intelligence. This one's going to be a little bit more general in nature and on the topic of deep learning. It's something I'm sure everybody's heard of. It's popular. Large language models have definitely done what 20 plus more years of research couldn't do, which make it very cool and exciting. So anyway, we've now got a lot of attention on especially a certain class of connectionist approaches, which is what deep learning is. And so let's take a little bit of time to go through what they are quickly, why we use them, why they're cool, and why maybe it took us so long to get where we're at today. We start with a simple feed-forward network. The name kind of implies it as what it is it only goes forward, and that's compared to and different from how most of our more advanced neural networks work. There's almost always some form of propagation of error, and in particular, it's back propagation, where after you've done the essentially prediction as part of the training, you figure out how well you're doing and then try to adjust. And so you attempt to send back this proportional error. All this came about because of our attempts to understand how the brain works. And these slides are coming out of the AIML Berkeley lab. If I cannot hit the space bar and go through all the slides at once. To them's the credit. They are good stuff. And so with that, we're back to where we were. So the way that neural networks work to some extent is based upon how we thought the brain and nerves worked quite a few years ago. Turns out that maybe not so close, but it is an interesting way of solving the problem. So the basic, I guess the important part that was taken away was that the realization that the human brain has lots of neurons. And we also have all of these things connecting together in various patterns. So it would be a realistic thing to understand that to approach something like human intelligence, or something that is at least I guess functioning as we want it to, based upon its goals and it's acting in a rational fashion, then it's going to take a fair amount of computational resources. Now, we've talked about what it means to be artificially intelligent, or to try for computational intelligence. So these sort of approaches will help with that, so that at the point that maybe it's good enough to pass the Turing test, in some ways we may be approaching that with a bit of a little bit of a challenge, in that most of these large language models don't really understand what they're doing. It happens that through some clever encoding and decoding and some interesting algorithm applications, that you get some good output. But as far as like a logical inference sort of thing, that's not what's going on. So one of the key and fundamental elements that we have inside of a neural network is a McCulloch-Pitts unit. And it's basically what the pattern for neural networks is, even largely today. You've got a collection of weights that are going in. You've got some sort of bias, so a way of essentially moving something around on the line. So introducing a way of kind of adjusting things more directly in addition to the weights. Then you've got some sort of a means of doing an input function, an activation function, then output. So when we talk about functions, in particular activation functions, we're talking about how do we get from the place where we've taken all this input from all of these various vectors that are coming in, we've applied some weights to them, and that it turns out being is a lot of basically matrix multiplication. So you're multiplying a lot of matrices together, hence why GPUs become really cool and important for that kind of work. So as we're doing all that, you've got to then decide, how do I know when it's on, right? Because a lot of times we go down to nerves as firing or not, is how we think of them. Now that's more complicated, and that's why you'll likely have a more interesting activation function and an output function potentially as well. But it is the basic thing of, it could be it's all or nothing. So it's off, it's off, it's off, now it's on, right? And that's what you see on the left side. And that's a very, it's a step function. It's a steep way of making the adjustment. A sigmoid function is maybe a little less harsh. Sigmoid off of the sine wave. You can see it there if you look at it. It's basically the beginning and ending of it. And so the basic idea is that you're going to reach some threshold, which will be the activation threshold. And at that point, you're going to essentially come on. And we adjust those weights, and it essentially moves the threshold around, just as the bias kind of moves things around. We can implement all the kind of typical logical functions, at least the very simplistic ones of ands, or, and not. I don't say all of them because there's some more interesting ones that maybe not. It says every Boolean can be, so usually exclusive OR gives us some grief is the only one, and there's probably some interesting way of doing that. When we talk about a feed-forward network example, you've got some inputs coming in. In this case, we've got 1 and 2. That's something that's going to have a value, and it'll be across some range. And generally speaking, we take all of those and get them to the same ranges. So we do kind of this normalization phase that takes things that range from different ranges, literally, and take them to where they're going to be on the same scale, so that it's not going to have one of the inputs skewing the results just because of the scale of the input, or essentially its units of measure could throw things off. So then you have those weights that are producing those intermediate values that are then in turn being used to produce an output weight or an output value. So we've got that input flowing through, came in into the, with the values of say 1 and 2 as an example. We applied some weights, got some intermediate values of 3 and 4, somehow combine those together, and the output value becomes 5. So that's essentially kind of a way these work. And it all comes down to this magic that happens in the middle, because that's where all this essentially multiplication is going on. This is a bunch of matrix multiplication of taking whatever the inputs are, and it could be that input is a single value. It could be that it's a vector of some sort. It could be that it's a matrix. It could be something in higher even dimensional, right? So we take it in, we multiply some weights, we apply some biases, then we use some activation functions to decide what the output values will be. And that's basically how we do this. And learning is accomplished by changing those weights in an incremental fashion. And as a general kind of thing that you will hear about from a typical type of this neural network is your perceptron. The single layer perceptron is on the screen. It is a very simplistic version of some of this. No shared weights. All of the units operate independently. And there's also you're essentially moving around and changing the shape of that cliff there. So there's the steepness to it and kind of the orientation of how it's shaping and so on. So you're basically moving this stuff around in multiple dimensions. And we do that by adjusting those values. And more precisely, an intelligent algorithm does so to take the error that is being made and sending it across the various weights so that it can be a better answer given some input. And so with that, the perceptron is able to do pretty good stuff, everything but the exclusive OR. And you can generally do a certain amount of linear separation, right, as you can see there. So one of the things that we do whenever we're doing computations is sometimes represent them as a graph. And in particular, when you deal with things like distributed algorithms and things like Spark, as an example, we definitely use graphs. And it's a way of essentially saying what needs to be done. So what are the operations and what is the representation of those operations to perform some function. And you generally, it's all about getting data into a usable form. Sometimes it's straightforward, such as using some sort of one-hot encoding. But what it comes down to at the end of the day is like pictures or something is not terribly useful for a computer. So instead, we'll put them into some sort of other data representation. Another odd one is sometimes less resolution gives better results. So we'll also oftentimes downscale the images as well, both in terms of potentially making them grayscale as an example, and also maybe making them littler. One of the things that you can do with these sort of things is represent relatively complex operations, such as E is equal to A plus B times B plus 1, and signifying that those two need to be added up first rather than doing it without it. If you were to ignore the parentheses is what it's at. So to do that, the clauses become kind of separate parts of the tree, and then you have values that are going to propagate up, and the value potentially is going to if it were to make a change, it's going to change at the point it goes up, such as whenever E changes value down at the example below, it's going to 6. That means that if there was an E representation somewhere, it would be referring to this, all of them would point to from here to wherever they were being referred to. So anyway, a way of representing operations. It's something that is very important in all forms of computation in computer science, especially important in artificial intelligence. The computational graphs, kind of I talked through briefly what they are, but you can think of it as a combination of a mathematical graph. It is a collection of nodes and edges. A node is the circle, the edge is the line. Generally, edge is directional as well. So it's in this case, it's a directed acyclic graph. So it's a DAG is what we're likely constructing, because that's what that graphical representation would lead one to think. Now we're looking at an example. More complex example might show something else, such as whenever you move into more complex back propagation as an example, you can see it gets relatively complex relatively quickly. One of the nice reasons that we do these sort of graphs is it allows us to take advantage of some graph theories, such as things like neighborhoods and so on, so that you're able to potentially do things in more optimized ways than we might see on the surface ourselves. So we've talked about one kind of type of neural network, which is a feed-forward network, and in particular the perceptron. Convolutional neural networks is another revolutionary thing that came and went, to the point that we still use it. It just is no longer all that interesting because we understand it, or at least we're used to the outputs of it. Back quite a few years ago, people actually wrote letters with letters, like in notebooks or in notebook paper into a envelope, and you would write an address on the envelope and stick a stamp on it, and probably put your return address as well, and put it out in your mailbox, or you might even drop it off at the post office. So one of the things that goes into that address is a zip code, the postal code. In the United States, it starts as a 5-digit postal code, and can have leading zeros. So you can have a 00011 or something. That's a valid postal code. It's not a number, but it's a string starts with at least 5. Then you can have an optional 4 to be more precise. Anyway, those postal codes correspond to essentially distribution regions. Getting it to where it used to be a job. Let's say that we'll go there first. It used to be a job, and actually a fairly well-paying one. In fact, I remember training to work in the post office, trying to get one of those coveted jobs whenever I was a poor undergraduate college student. And what you did was look at an envelope and type in a number on a keypad. That was the job, and it printed out a barcode on the bottom of the envelope, and then that envelope went through the system automatically. Before that time, people sorted mail. They actually picked up the letter, put it where it went in a series of trays, or maybe an assembly line sort of thing, where things are coming down a conveyor belt, and you put it into one of 2 or more locations, maybe local versus not local. Anyway, now that we have this ability to read numbers, or we have the ability to sort based upon barcodes, then you need to go from written number to barcode. And that's what one of the things that convolutional neural networks did that was so revolutionary is they made it to where with a high degree of accuracy, they could read a postal code and be able to print out that barcode so that the machines could sort those envelopes, and the ever diminishing amount of postal mail that we have would be able to be more efficiently routed, reducing the cost supposedly. As you've seen, whenever that the volume of mail decreases rapidly, a lot of other costs go up. It becomes very expensive to send a letter. So convolutional neural networks made up of various things, including things like a kernel, the concept of a convolution, which is applying a kernel to a pixel. A pixel is kind of what you think a pixel is. It's a unit of the image. There's a receptive field. It's essentially the first layer in a convolutional neural network. So I need to fix the typo. And it's also, you have this concept of pools. Those are things that summarize the adjacent items from previous layers. And so the key piece that convolutional neural networks started throwing in is the concept of location and locality, and something being adjacent or regional across different ways. Because if you think about a typical process to convert a set of written numbers into some sort of graph or graphical representation or something a computer can read, it's going to basically take it and flatten it out across the row. That's one approach. But it's certainly not going to have it to where it knows the bounding of the letters and numbers. That's not something that at the time was doable. Anyway, to finish out our definitions, tensor is a multidimensional array of any number of dimensions. So it's a multidimensional array that has any number of dimensions associated with it. And a GPU is something that is sometimes runs tensor processing units as well. So GPUs, graphical processing unit. Sometimes you may have a tensor processing unit, and it's all about doing all that matrix multiplication that we're talking about. So when you compare a traditional three-layer network to a or compared to a traditional neural network anyway, generally speaking, you have an input layer and an output layer, and then you have one or more hidden layers for it to be considered a deep neural network. And so the basic idea is you can think of it as almost more of a cube approach. So a 3D volume is being computed onto it as well, utilizing a lot of times the color. So the color channels that are coming from images, red, blue, and green, turn those into something that gives you into a three-dimensional representation. And that's a convolutional neural network. Recurrent neural networks allow cycles. So is the main big difference. And the recurrent neural networks heads us down this long-term, short-term memory. Recurrent neural networks, which is a way of having a certain amount of memory with a gating unit controlling for how long something gets remembered. And then we have various ways of organizing our units. We've already talked about single forward or feed forward and multi-layer, multiple layers or single layers and those sort of architectures. You've also got the idea of having more interesting patterns inside of them, so that there may be what are essentially loops inside of it. And that's where a recurrent neural network is essentially being done. Compressing down by time of equal to 0, 1, 2, and so on. You can order your steps that are recursive in nature to be where they appear sequential over time, which allows you to get into some more interesting graphs as well. What do we use this stuff for? All kinds of stuff. Vision, computational recognition of either handwriting, which is the classic example, tracking of people, license plates, looking for detection of things, you name it. It may be even somebody's expression and mood that they're in. And you may also do it as far as things like translation of language into text and vice versa. Reinforcement learning, things like DeepMind and going and playing Go and winning. So lots of technologies, and not to mention the speech processing, natural language processing, including the large language model approaches that we're seeing that utilize the concentration sort of, or the idea of focusing on a topic for a moment. So anyway, with that, we'll wrap this up. If you have any questions, let me know. As always, stay safe. If you like this stuff, give me a thumbs up, like, and subscribe. And YouTube would be cool as well. Stay safe. We'll talk again soon.